All right, let's work. So I have good news. We have no exam this week. We'll still have a quiz, but this is a week off from an exam. This pace is breathless. We do have, it's my turn. We do have an MP due on Friday. Now, I want to give you fair warning. Let's see, how can I do this? Raise your hand if you were on the queue a week ago last Friday when MP2 was due, the last day. If you spent time on the queue the last day that MP2 was due, raise your hand real high so I can see. I'm guessing about 20% of you is my guess, okay? Let me ask you this. Bart, how was it on the queue 2 weeks ago now, or almost 2 weeks ago? How was it?
Awful.
It was a long wait. Now, we don't, as much as we'd like to say, oh, don't worry, it gets better, it doesn't get better in this case because MP3 is actually a lot longer and requires more debugging cycles than MP2. So, don't expect to get quick service debugging assistance on Friday. It just doesn't happen. It breaks my heart, but we don't know how to do it, or none of the solutions that we have seem to make sense. So really, really, really work early. Aren't we chatty today? Okay. So the other little announcement is that we will do Lecture Helper again today. And I owe you all a blanket apology because I was not answering questions because I was looking at the wrong part. It was totally user error. So I was not ignoring your questions. There were a bunch of them actually. I just didn't see them. Now I know where to look. Right, so I should just go all questions all the time, right? Yeah, okay. Okay. All right, so I'll be better about it today. So let's work. We're going to make a transition today from our first abstract data type list into our next abstract data type. But first I want to do kind of a summary of some of the things that we've observed in the context of implementing things for lists. This table is meant not necessarily to be an exhaustive table for memorizing, but rather to just help you remember the thought processes that we went through. So here's what I want you to do. First of all, I want you to understand what the table is intended to hold, and then I'm going to tell you that actually some of those entries aren't accurate. So first, let me tell you what the table is intended to hold. Starting with insert and remove at the front of the list. What I mean here is at position 1, specifically in the list interface at position 1. So by front, I mean position, position 1, or location 1. First thing in the list. In the second analyses, when I say a given location, in the context of a list, I mean like this. So I'm just going to draw a little diagram and I'll show you what I mean. Okay? So if this is your list, and I want to insert here between the second to the last one and the last one, excuse me, by saying a given location, you can assume that I'm going to give you a pointer to the one after which I want the new one. Okay? So it's after a given location, and the given location that I'm going to give you is the pointer before. Okay? On the other hand, remove at a given location. By remove at a given location, I mean remove exactly the one that I'm pointing to. Okay, so I'm going to give you a pointer to the one that needs to be removed. So that's what those mean. In the context of the array, I'm going to give you specifically the new position, say 3, for example. And you can consider that to be fixed and known. And similarly for remove, I want you to either insert the third thing or remove the third thing. In contrast, insert and remove at an arbitrary location means that the location is parameterized. That is, when we're analyzing the running times, the worst case running times, we're going to assume that our biggest enemy is choosing the value of the parameter. Okay? And it may change. So it's the worst choice for a parameter where your algorithm has to work for all parameters. Okay, so arbitrary means parameterized. All right, so here's what I want you to do. I want you to spend the first 45 seconds looking at the left column here at running times for singly linked lists and look for errors, and then the next 45 seconds looking at the array column looking for errors, okay? So on your mark, 45 seconds from now. Here. Okay. So what I want you to do is raise your hand and use your fingers to tell me how many errors you think there are. So if you think there are no errors and this whole thing is just a joke, raise your hand with 0. If you think there's 1, 2, 3, or 4, or 5, 12, oh wait. Okay, raise them high so I can see. I'm like doing average over this. Okay, so when I look here, I see that the average is 2.5. I don't know how many errors that is. Somewhere between 2 and 3. All right, so here's how I want to do this. I'm going to start. I'm not going to tell you how many till we're done. I'm going to start here, tracing down the page with my ink, and I want you to tell me to stop when you think there's an error, okay? So I'm going to start up here, and I'm going to walk down, going for a walk, just like I really wish I were doing, and you tell me when you think there's an error in the chart. Yeah, just for the left side. We're going to walk up the other way. Right there? Okay, all right. I'll stop there. So what's the deal there? You think this is big O of n, but I'm gonna parameterize where it is that we need to do it, right? Where it is, why? What's the explanation for that? How would you describe what we have to do? Yeah? You want to tell me? Yes? Oh, right, I forgot that part. Look, even if I tell you the location of the thing that I want to remove in an array, or I'm sorry, in a linked list, you have to walk down the linked list to that location. You can't get there super fast like you can for an array. So this is big O of n to find. Okay? Similarly for removal at an arbitrary location. You can't get to the place you need to remove efficiently. Okay, any questions about anything in that column? All right, let's do a U-turn then and start heading up the other column. Everything okay so far? It's okay? Stop? Okay, fine. Come on. I don't have to go finding it, right? If I tell you every time, every insert that's ever going to happen into this is always in the third place, doesn't that mean we can do this efficiently? Why? Oh, I'm inserting, not replacing. That's right. That means because of the way that we've defined this, we have to shift things out of the way. And it's that process of shifting that makes this big O of n. Okay? Even if we're always doing it in the same place, we still would have to shift. Okay, fine. Let's continue our walk. There's only one place left. Really? Okay. Well, let's talk about this one for just a minute. Do you know what this is? It's a fish. It's a special kind of fish. Do you know what kind of fish it is? It's not a goldfish. It's obviously not gold. It's a red herring. That's right. Very good. This is a red herring. That means it is, and it's something that's not an error that looks like an error because I want us to have this conversation, okay? I wanted you to think of this as, ooh, I don't think that's right. But in fact, it brings up the following conversation. When we use an array to implement a list, we do the following very smart thing. We build our array. I'm just going to make a little array here. Assume it's big enough. Here's the array, complete with its indices. And we say, oh, look, 0's kind of close to 1, so I'm going to put the first thing in the array 0. Like, oh, I don't know, what should I put in my arrays? I should put fish there. That's a blue fish. Okay. All right. Now I'm going to put another fish here. This is a whale. I don't know. No, I'm not going to do that. Okay. So we make our list of fish like this. And when we refer to the first one, we go, oh, I know. We should just have that first fish be in position 0. Okay? But we didn't have to do that. We could have taken our ordered collection of fish, our 1, 2, 3 of fish, and flipped it around so that the first fish is actually out here somewhere, out in the end of the memory, and our last fish was in position 0. Okay, so let me do that really quick. The middle one happens to stay the same, and this is going to be silly because I don't know what those fish look like. I don't know. But now, this is the first fish, this is the second fish, and this is the third fish. Okay? Now look what happens when we try to insert in the first position. Can we do it? Is there space for it? Where should we put it? Yeah, we're going to put our red herring here, right? No shifting necessary. Ew. What if we want to remove from that first position? How do we do it? Just get rid of it, right? All we need to do this is keep track of how many fish we have in our array. If we know that, then we know where is the next available slot, right? Any question about that at all? So, the punchline is that we took memory and used it in kind of a counterintuitive way so as to improve our running time for this particular example. Okay? Any question about that at all? And it was a little bit of a red herring. I wanted to have the conversation about it, and maybe you'll see why later. Okay? Do we need to initialize it with extra space? Oh, great question. Okay, so there is this sort of this dangling issue of using arrays at all. And that issue is, well, what if the array fills? And I'll tell you right now that we're going to spend a whole lecture on the question of what if the array fills? But we're going to do it next time. Okay, so let the suspense build up, and we'll answer it on Wednesday. But for now, we're going to assume that our array is big enough for right now. Okay? All right, any other questions about this? So for right now, our array is plenty big. We'll see later, see that in action in a little bit. Is it good? Okay, so this is it. This is kind of all I have to say about lists at this point. I'm going to turn the chapter to our next abstract data type, and that is abstract data type stack. Okay? Here's how I think of stacks. Stacks are merely the programmatic manifestation of a Pez dispenser. Now raise your hand if you've never experienced a Pez dispenser. Okay, you need to know not only what this sounds like, but also what it feels like. It's very unique. It's a unique thing. Remind me, and I'm going to pass these around so you get that experience, because it's really kind of key to your cultural upbringing, okay? Not even kidding. Okay, so I'm going to use it for just a second. So here's the thing with a Pez dispenser. First of all, what's a Pez dispenser filled with? Candy. This one isn't, sadly. I know, I'm a loser. Like, the least we could do is fill it with candy, right? Okay, now let me ask you this. Those of you who have experience with Pez dispensers, suppose what's your favorite Pez color? Just say a color, it doesn't matter. Blue, okay? What happens if the blue Pez is way down here? Okay, the only blue Pez in the whole thing is way down here. What happens? What happens? How do you get the blue candy? Yeah? Yeah. You have to take all the candy that's on top of it out. The only access that you have to the candy is right through this interface. Okay, you pop the head back and it gives you a piece of candy. The only way to get the next piece of candy is to eat the one above, all right? The internal schematic for a Pez dispenser is right here. Okay, so this is what they look like on the inside. Now, the way I want to describe it is as a metaphor for data. So each piece of candy is a data element. And what you observe about it is just as the candy is all lined up, the data comes in linear order. That is, every piece of candy has a next piece of candy. They're adjacent to one another. And moreover, just as we constrain the access to the candy through the top of the device, we are going to constrain the access to our data to one end of the structure in which it resides. Okay, so now I missed a question. It was a good one. Okay, so now imagine that this is all of your data. This is all of your data. It's all lined up. We're not talking about the structure of memory necessarily. It's only the model for how you can access it. And here's what you can access at any given time. And moreover, if you're putting data into the structure, the only place you can do so is right here. The way I'm going to describe this stack is as a constrained access linear structure. And the ADT looks like this. It has a function for inserting and a function for removing called, the insert is called push, and the remove is called pop. So we're going to push an element and we're going to pop something, and pop is going to return an element, not EPOP, though that sounds good. Okay, so this is what the interface looks like. You can push something in, you can pop something out or off, and that's it pretty much. There's only one other function of convenience that we provide, and that is the ability to check to see whether the stack is empty. And we provide that to the client. We'll talk a little bit about that implementation later. Okay, are there any questions at this point? It's all kind of fuzzy and fluffy, so I don't know what kind of questions I could even answer here. I wanted to give you a very brief application of it, however, because this is not the first day where we've said the word stack. When else did we say stack? Stack, memory, that's right. The heck, gosh, I didn't know that this was going to come up again. So I want to take just a second to control the two. So guess what? The process, the data structure that supports the execution of your functions is an abstract data type stack. It's a stack. It's implemented as a stack. So I want to take a second and show you very roughly a very broad caricature about how that works. So consider the code that I have written for you, or pseudocode, or at least the function call pattern that I have written for you here. So I've written a function called main, and main calls two functions. What are they? Main calls two functions. What do you think I intend? Study hard and do good work. That's right. Now, what does study hard do? Study hard calls MPs and exams. That's right, and quizzes and problem of the day and okay. And MPs calls plan and code. Okay, so that's how this is intended to work. Here's roughly what's going on in memory. There is this notion of a stack implemented in memory for you, but it's encapsulated away. You don't need to know exactly how it works. The system takes care of it, but here's what's happening. You call function main, and on the stack, the function main and all of its parameters and all of its variables are placed, or I actually should say pushed. So all of the variables and all the parameters for function main are pushed on the stack, and execution begins. Execution gets to study hard, and without removing any of the memory associated with main, the new memory, study hard, is added to the stack or pushed on the stack. I'm going to call it study hard, and it's variables and params. Mains, variables, and params. And execution continues through study hard, and when it gets to MPs, whoa, those are big. All of MPs, variables and parameters, are pushed on the stack. MPs calls plan. So plan Nobody does much planning. Okay? Then plan completes execution. Okay, so function plan completes execution, and it together with its variables and parameters is popped from the stack. So what's on the top of the stack now? The green candy. I mean, yeah, MPs. I'm mixing metaphors here, right? The MPs are at the top of the stack. Okay? Then we're not done with MPs, because then we hit function code. And all the variables and parameters of code are put on the stack, etc. Okay? Now, I think I won't keep going. The value here is in recognizing that the system is deciding for you. The system is deciding for you how that stack is used, right? You're pushing something, it's pushing something on for you, which is all of the memory, all the values that you need at that point. Now, I have a question for you about MP3. Raise your hand if you tried to solve reverse recursively. How'd it go? Were you able to do it? Could you solve reverse recursively? Wait, say it louder. Okay. Did you try it with the test cases? Oh, and it passed the test cases? Okay. Did you try it with the test cases? Did you try it? Did it work out? Kind of? So I tried it. Okay. I won't put the pressure on you guys. You guys are probably much better coders than I am. I tried it, and I got a Stack Overflow when I tried to solve the reverse problem recursively, because every recursive call that happens, a new stack frame is created. And I don't know, I didn't have enough memory for that. And so I went, that is what Stack Overflow means, right? That is what's happening when you exhaust your stack memory, okay? All right, so I actually don't remember whether or not it's possible to solve MP3 recursively, the reverse recursively. Yes?
It also happened when I was trying to test
the merge function?
no, the lab memory.
Oh, lab memory as well, maybe.
Because there was like find R, which is
Okay. Yeah, so this is what's going on. When you hit a Stack Overflow, you've just got too much stuff on the stack. So what that means is you can economize by making sure your parameters themselves are small, making sure you're not making copies of data inside the scope. Then each one of these little boxes is smaller, so you're taking up less of your stack. Anyway, it's not part of this course to talk about the details. I just wanted to demystify the use of the word stack for you, that there is this data structure that is used. Okay, there are two other extremely common examples that I'm going to leave to you to go look up. And if you would like to know more about them, you should post to the Piazza, and we'll give you more verbiage than you've ever wanted. But I think there are probably like 3-minute YouTube videos, which will make it much more entertaining than I ever would. So, one of the examples is balancing brackets, balancing bracketry in writing code. So, this process of making sure that you have your parentheses and your brackets matched as you write code employs a stack behind the scenes. And you can kind of see how it works. If you see a left bracket, you push it on the stack. If you see a right bracket, you pop from the stack, make sure they are a pair, and keep going. Okay, so push left brackets, pop on right, make sure they are a pair. If you want more explanation than that, please do the research. Google is your friend. Similarly, postfix, expression evaluation, goes something like this. If you see a number, push it on the stack. I'm going to use that twice. If you see an operator, and it's a binary operator, pop twice, do the math, push the result. Okay, so the result of these three things is equivalent to a 9. Okay, and that gets pushed on. Again, I'm going to leave it to you to go and find, you can find a web app that emulates this for you and that animates it for you. It's very cool. All right, any questions about this? All right, so this is a new abstract data type, as I said, so we better talk about it from a programmatic perspective. Just as I promised, we are going to use our class definition as the description of the abstract data type. And as I said before, we're going to have a push and a pop. Furthermore, there is this function empty that returns true if there are no elements in the stack. Now, this bears a little bit of conversation. If I make this available to the client to use, I'm going to expect them to use it. And as such, I'm going to absolve myself from having to play defense against popping an empty stack, okay? So in our implementation, we're going to assume that the stack is not empty. Now, would you ever really do this in real life? No, you'd have some kind of more elegant exception handling. But for the purposes of thinking about the stack, we're going to give the responsibility of checking for empty to the client code, and we're not going to clutter up our code with it, okay? All right, so in the interest of kind of getting some ideas for what that question mark might be there, I want to very, very quickly go through how these things might be used in code, okay? So here's pseudocode for the deployment. You can assume that I have declared a stack of integers whose name is S, and then each one of these is actually an S dot, okay? Now I'm going to just draw a picture here. It doesn't really have anything to do with memory. And I'm going to push a 3, push an 8, push a 4, pop. What do you think I get back when I pop? Yeah, it returns a 4, and the new top of the stack is the 8, okay? I pop again, returns an 8, and the new top of the stack is 3. Then we push a 6, and I'm feeling the need to erase. We push a 6, etc. Okay, I'm not going to finish this. Okay? All right, so now we've thought about this a minute. My question is, what's that? Don't peek. Caught you, Vern. Just kidding. What do you think is there? You can describe it using the structure rather than the variables if you like. What do you think it is? How are we going to implement this thing? How would you describe an idea for implementing this? Yeah? Maybe an array. Great idea. An array is a good idea. I'm going to, for the moment, push that on the stack and ask you for another idea. Yeah? Do you have an idea? Yeah, heap memory, and how do we use heap memory in this context? Yeah? A linked list, that's right. Right, okay, so we could implement this using a stack, which I pushed on the stack because of the order of my slides, or we could implement it as a linked list. And that's the one we're going to choose for the moment. Now, these are not the only two alternatives for implementing this thing. In fact, I believe in lab, let's see, you use an abstract you use a standard template library list to implement a stack, I believe. And in the MP, you implement, yeah, I can't remember. There are lots of varieties, and we'll ask you to do more. So we're just looking at 2 different implementations here. Okay, I think nothing about this is going to surprise you. It's a stack. It's got a node in it. I happen to call it a stack node. One of these days, these things are going to just turn into nodes. What you'll notice is missing. What you'll notice is missing is constructors here. Assume any constructor that you want for those nodes exists, and we'll deploy them just whenever it's convenient to do so. Notice that we're going to keep hold of the top. That is right here. This is the top. And that data in this form will have arisen from a sequence of 3 pushes, at least. Okay? So we push 4, then we push 6, then we push 3, for example, to get memory into this configuration. Okay, so here's what I want to do. I actually want to spend a few minutes writing the code for POP. Now, the reason I want to do this in detail is because it's a review of how to manipulate lists. So let's do it. Okay, first of all, and there's one more thing, and that is we're going to maintain size. So at this point, if we've done that, size is going to have value 3, okay? As we put something in the stack, we'll increment it. As we remove something, we'll decrement it. Okay, so what does POP look like? Again, we're going to assume that the stack is not empty. We're going to leave the responsibility for checking to the client. And so our code has to do the following. It needs to grab hold of the top element and make note of its value, make note of its data, because that's what we're going to return. We're going to return a 3. Okay? Then we're going to move the top to the next element. Then we're going to return the original top data. Am I missing anything? I'll give you a hint. Yeah? Excellent. So we're going to free the memory for the original top node. What else? There's one more thing missing about this code. Yeah? What if the top is empty? We're going to push that to the client to decide. Okay? So the client code has to check. And the answer to that is, if it's empty, we're going to get a segfault. Okay? If this were a slightly different class, we would be exception handling, but we're not going to bother here. Yeah? Yeah, very good. Decrement size. Okay, this code is practically written. The first one is 2 lines of code, and the other 4 of them are a line of code each. So do you want to race? Let's do it. Okay, on your mark, get set, go. Oh, I almost died there. Done. Who won? Okay. So there are 2 lines of code for the first one and then 1 line of code for each of the other things. I have no idea whether it's correct. So I believe that it acts like this. List node pointer T gets the value of top. Here's T. I'm going to grab hold of T's data. So I'm going to set aside 3 here in this thing called retval. I'm going to increment top to be top next. So it'll go like this. I'm going to delete T. Then decrement the size, so it would go from 3 to 2, and then I'm going to return 3. Okay? So I believe this is okay code. And again, I know if the stack is empty, we're going to get a seg fault. I know that. Yep. Count me in. Okay? All right, any questions about it? I have a question for you. What question do you think I'm going to ask next? Oh, you're so meta. Question do you think I'm going to ask? I've just written this piece of code. It implements part of an abstract data type. I have no idea whether it's good code or not. So what are the questions I'm going to ask about it? There are 2 questions I'm always going to ask of the code. Does it work? And what's its running time? That is it correct? What's its running time? In this class, in a very few cases, we're going to prove that the code that we write is correct. Okay? Not here. We're almost always going to be pretty careful in discussing the running time of the code. So I'll ask you, what's the running time of that code? Asymptotic running time. Constant, O of 1, good, same thing. Good. It runs in constant time. How do I know this? Well, I look at it. There are no loops or recursive calls, right? It's essentially just a sequence of assignment statements and some memory trickery, right? So there's really nothing that's going to take time proportional to the size of the chain there. So it's constant running time. Good. Oh, I meant to write it right. Meant to write it right there. Okay. So pushing is a function that's written right here. It actually has a bug there. Now I don't think it is. You need to increment the size if you push into the structure. And I'm actually not going to spend time going over this code because it's exactly the same as a function that you've written before, where that function was called insert at front, right? Or insert front. So you know how to do this already. Let's move on. All right. Any questions then about implementing a stack using a linked list? Okay, so I'm going to pop that discussion from the discussion stack. And all of a sudden we have the implementation as an array. Open for discussion. Okay? First thing, make sure you believe that the private members you see here are a representation of a dynamic array. Do you believe it? Make sure you believe it. So what's going on here is the constructor will use this pointer to allocate a contiguous section of memory. Oh, look, just like this. The constructor will create an array for items. So items is really just an array. Capacity is, well, it's the capacity. It's the number of entries in the array, or that can be in the array. And size is the number of entries that are actually in the stack. Okay? So size will always be less than or equal to capacity here. All right? Any questions about that so far? The constructor is here. By default, it makes an array of size 4 that initially contains nothing. Okay? So the stack initially is empty. All right. So here's a little picture of the stack. And what I want to know from you is where array index 0 is in this stack. Where's the 0? Where's the 0th index in the stack? Where do I put the 0? So arrays have, or I'll make it, doesn't even matter. So the question is, does my array do this, 0, 1, 2, or does it do this, 0, 1, 2? Option 1, raise your hand if you think option 1. Raise your hand if you think option 2. Okay, it's option 1. So here's what we're going to do. We are going to put the bottom of the stack. I wanted you to do gymnastics here. I know that you kind of want to do this, right? The bottom of the stack is going to be in the 0th element of the array because all the action that we're going to do is at the top of the stack, right? All the action, the pushing and the popping, is all out here where we may have plenty of space, okay? So now, what does that mean about this entry? Where is it? Oh, look, the top of the stack is always in items sub size -1, right? There are 3 elements. 8 is in position 2. Whoa, whoa. Okay, any question about it? Okay, so there's one last little thing I want to point out, and that is the thing that's bugging you. The thing that's bugging you is what happens if, how many things you want to put in your stack? What if you want to put 7 things in your stack, right? What happens if your array fills? This stack can only hold 4 things. It's not a very helpful stack. So let's take a look at how push operates here. It's the first question we address. If the size is at capacity or worse, it never will be worse, but if it's at capacity, we're going to grow the array somehow. Otherwise, we're simply going to plunk the new data into the next place, which would be here, and then increment size. And that's it. That's all we have to do. Now, the problem is we don't know what this looks like. The somehow is a mystery. Are you worried about it? Keep calm, carry on. I think you should be a little bit worried about it. You should be a little bit worried about it. We're going to spend about a whole lecture talking about it, so it's worth worrying about. And that's it. That's the cliffhanger. Hey, what's up? It's a koru. It's the Maori symbols for family. Oh. My siblings and I all have them, and my parents all have them. What's even cooler is the fact that I, the goody two-shoes oldest sibling, went with my crazy younger siblings to a tattoo parlor in Las Vegas and got it done. Oh, yeah, sorry. So an array list is a Java thing. Yeah, we don't have it, but we do have vectors, and we could use vectors, in which case we wouldn't have to worry about it. It's similar. But what's going on behind the scenes of a vector is what we're going to talk about. So the grow the array issue comes up with every linear structure that you ever have, and the same solution applies to all of them. So even if we used a vector there and we didn't have to worry about it, inside the vector, they have to worry about it. Does that make sense? Okay. at the start. Yeah.
So it's the custom range.
Yeah.
I think it depends on the number of the items in the array.
Not for inserting at the front. Inserting at the front will always be constant time because you know where the front is.
So
You don't have to
include
shift
the
it.
switching time.
Right. You don't have to switch because you're going to keep it this way. It'll always be this way. You don't switch and then do it. It's you leave it switched.
So we only consider the time to put the item on the last
Right.
or the start after the switching start.
You never switch. There is no switching. That's what's missing. I can see. There is no switching. You're gonna have it when you insert the first thing. Where are you gonna put it?
So after switching, we start considering the time.
No, there's no switching. Okay, it's an empty array. We're gonna get this. You'll get it. Okay, it's an empty array. Where are you gonna put the first thing at the front? Insert into the front of the list. Where does it go? Yeah. Now insert into the front again. Where does it go? No. Yeah. Now insert in the front again. Where does it go? Yeah. So there was never any flipping. Yeah. There was never any flipping. You're gonna keep it backwards the whole time.
So the other items is row 1, 2, 1, 2, 3.
Yeah.
So we do have this time when we serve.
So it ends up, you can think about this, but it ends up not affecting any of these. These all stay the same running time. You have to go the other direction with them, but they all stay the same running time. You have to shift forward instead of shifting backwards. Does that make sense? Yep.
So I have a question about it. So in C++, when you create an array, you have to know the size of the array, right?
Yeah. There's nothing automatically that tells you the size.
Yes, but so I try to create an array with the size I, and that I should like equal to the length of the list node. So, but it won't compile.
Is this for LabGB?
No, that's for the MP last week.
So it's hard to address compiler errors like without looking at the code. So the question is, what's i's value?
Yes, but like every time you put in a new list, the length is going to be different. So I try to insert that the array, the constructor of the.
So is it a dynamic array or a static array? So you can't.
I see. Start here.